Okay, so I have the pleasure to have Juhan Aru from EPFL, who's going to talk about correlation function for CLE4.
Okay, yeah. Hello, everyone. Good morning. Thanks very much for coming on this beautiful day. So that's why I put the yellow background. I thought a bit of sun-like thing is also good for the morning. So this program sounds great. I just arrived. I'm looking forward to all of it. I know that there are many types of mathematicians, physicists here, more algebraic, topological, more physics, probability. And then probably there are also several categories, more serious, less serious. So I'm in the category of probability and very much non-serious, very naive category. So this will also be the style of this talk. Okay. So first, just to put us all on the same page, I will talk about different kinds of random objects. And when I talk about random objects, I mean just a probability measure on some space. So the space could be just R, it could be Rn, it could be space of functions, etc. But it always will be a nice Polish space, and you can equip it with its Borel sigma algebra. And when I talk about random object, this, if you want, you can think of it as just a corresponding probability measure on that space. So, yeah.
Sorry.
That was not a question. I thought that's good. It's not. You know, we don't like all, at least me, I don't like all random objects. I like those which have some nice properties, like when you do algebra, etc. You might maybe like objects that have certain symmetry, certain extra properties. And in probability also, there is some of these measures stand out. Okay, so for example, you can talk about probability measures really in Rn, random vectors. And then if you put two natural conditions, one that this probability law is rotation invariant, and the other that the coordinates are independent, then in fact there is only one, basically up to multiplicative constant, there's only one measure that satisfies that. Okay, so this is, I find already quite nice and goes back to Maxwell. If you go to slightly more complicated objects like continuous functions parameterized by the positive real axis, then you can characterize Brownian motion as only random continuous functions that has stationary independent increments, in the sense that if I look at the path starting from some point t, I shift it back to 0 and I look at the future, then I have another random object indexed by the positive half line, and this will have exactly the same law. It will give you the same probability measure. Okay, so this is some consistency conditioner for the probability measure if you want some statistical symmetry. You've already seen SLE, I assume. I guess Evelina has talked about it. This you can kind of see in a similar way. You can also see it as a probability measure now on random continuous curves in say simply connected domains with two boundary points fixed, and it also you can characterize it by via some simple properties. One would be conformal invariance, and the other would be in a similar way stationary independent increments. Only you translate it here in a geometric sense, in the sense that if you have observed the curve up to some time, then in the slip domain, when deprived of this curve, the other curve will have the same law. And of course, here to be able to talk about the same law, you will have to first map it back using the Riemann mapping theorem so that you parameterize everything in the same way. Okay, so this is an overall theme in probability that some objects are kind of nicer, and these are often signs of universality, meaning that such objects pop up in many different contexts. Okay, and if you are more maybe algebraically minded, then CFT was another sign of universality, right? When it was studied, this was used as an explanation in 2D statistical models as the universality of the scaling limits, the fact that there was this rigid algebraic structure. And here we also have a rigid structure, but it's just seen in a probabilistic way. So the topic of today is conformal loop ensembles, or CLE. So here are two simulations by David Wilson. I believe you've also heard about it in the talks of probably Antoine and maybe also Evelina, but I will try to introduce it again in a certain way. So here, as I said, you can also think of it as another random object, a natural random object. And in fact, you can do it in several ways. Okay, you could think of it as a random collection of closed loops. And maybe on this image it's not so clear what are the loops, but these are the boundaries of the connected components of the complement. And you can build a nice space where you can talk about probability measures on those. Or if you wish, you can also look at it as a random fractal carpet when you really look at this closed set itself. In some parameter range, these two viewpoints are equivalent. In another parameter range, or in some settings, you really want to look at it in the first way. Okay, so and here, as I said, loops are the boundaries of holes, and these are described by SLE kappa processes that you have heard about already. Again, this has a nice simple characterization. And you can bring it back again to, in some sense, a stationary increment property, a geometric property that if you have discovered certain loops, for example, that touch a closed set, then you look at all these loops in the complement, there will be some holes. And if these holes are simply connected, you will in fact, you can ask what is the object I see there in terms of loops. You will see some loops. And you just ask this to be also the law have the same law. Okay, so it could be, for example, that I look at all the loops that that's this one, and then maybe I have inside here a simply connected domain, and then I just ask what is the law of the loop collection here, and then I prescribe that this has to have the same law. Again, this gives some consistency condition for this probability law on the family of loops. And it comes out that this consistency condition actually allows for just one parameter family of such random objects. Okay, any questions so far? Okay, so one thing you might wonder is how do we mathematically construct CLE? So it was introduced by Scott Sheffield in 2005 or 2006, something like this. And the first thing you can do is to try to construct all these loops by actually using just these SLE explorations, but you kind of modify them a little bit to make loops, and if they cut out the part of the domain, you start another exploration there. Okay, so this is there is one way to make this precise using really this just exploration processes. There is another way to do, which is using what is called the Brownian loop soup. I don't know if you've met the Brownian loop soup this week or not.
No, no.
Okay, so this would be another object that probabilists like. So I talked about Brownian motion, and you in 1D, but you could also look at the Brownian motion in 2D, which would just also kind of infinitesimally decide all the time, do I go left, do I go right, and do it with the, or up and down and do it with equal probability. And then as soon as you have a Brownian motion, you can talk about Brownian loops. Okay, you have some starting point, and then you fix some time, and you let the Brownian loop run, and you ask it to come back at time t. And then you can build a measure on all possible loops in your domain, for example. Okay, and this means you roughly that you take all kinds of starting points, all kinds of time, and you put some weight on them. And then the loop soup would be just taking sampling a countable collection from this measure. Okay, so this is called the Poisson point process. This is how we deal with infinite measures, how we sample from infinite measures. And this would just mean that I actually put on the on my disk some collection of these Brownian loops. And then I can look at their geometry. And for example, if I look at outermost clusters and their outermost boundaries, they again give at least one parameter range of this CL.
So the starting point is chosen uniformly.
Uniform, yes, yes. Okay, So this would be two ways to define it directly in criticality. In some cases, we can also do it from the discrete. We start from a statistical physics model on the lattice, and we take continuum limits. So for this is a case for the percolation, where I recall we have these pluses, minuses, okay, and so maybe rather we want to do it on the triangular lattice in this case. We have pluses, minuses here. These define some clusters. And when I look at all cluster boundaries, then this has been proved to converge to CLE6. The Ising case is another case where you have proven. In fact, there we already see that there are two different CLEs that appear for one single model. CLE3 that we get when we look at the spins of the Ising model and look at these boundaries. And CLE16/3 should be, there's a typo, when we look at what is called FK Ising, or a percolation representation of the Ising model. Okay, so there are other ways you can start from random walk loop suit boundaries. And in the case kappa equals to 4, you can see the certain level lines of a certain random field, and I will come back to it. Okay, so one thing that will be a bit important for us is that there is also a nested version. In fact, if you followed what I was saying for percolation, you saw that this cannot really be the outermost clusters only, because I will have clusters where I have pluses and then minuses inside the cluster. And then I will have to have loops here and then a nested loop inside. So there is a nested version of this CLE where I start in the disk, for example, with some loops, and then I just replicate the same process inside each of these loops. And here, these iterated loops will represent the cluster boundaries in, say, a FK Ising model. And what is important for us that the fractal carpets themselves also have an important meaning. They correspond to clusters themselves. Okay. And if you think of this, then so the percolation representation of the spin models, they encode the correlations in a geometric way. So what they do is that you have some spin correlation that you're interested in calculating, and this will translate into the probability that the 2 points are in the same cluster. Okay, so it translates these correlation functions to a geometric variable, and so calculating spin functions can be seen as just a correlation spin function as seeing as some geometric observables on these certain CLE cascades. Okay, so there have been some questions in there about these CLE for some time, starting from the beginning of their, I guess, founding in the middle of 2000. And that's a question of, is there some sort of, can you talk of some sort of CFT of CLE or SLE, and in what sense, what type of algebraic structure could you find? Okay, and I guess there are some motivations for it. One is, as I said, that the CLE or SLE, they encode similarly universality of scaling limits like CFT, so they do also have certain confining properties. They also have special properties at certain values of kappa that correspond to certain central charges, etc. Okay, and there have been many links between SLE and CFT starting from the beginning of it. We saw that at least spin and spin correlations are naturally geometrically encoded. And in fact, in the physics literature, there is a very interesting story, which I wish I understood better, where Raul has written some interesting things, and where they managed to really disentangle some of these correlations using bootstrap approaches, using cases for the intermediate spectrum, etc. And for me, it's still, when I read this story, it feels like reading an interesting novel in a language I don't fully understand. You can sense the beauty of it, but you cannot grasp the syntax fully. Okay, but probabilistically and in a rigorous way, there has also been recent progress. One is calculating some specific things, for example, 3-point functions on CLE kappa and refining certain family formulas from the physics literature, or actually what Antoine was talking about, I believe, on Monday, which is finding some reminiscence of the CFT structure, at least some representations of the Virasoro algebra on the CLE loop. Okay, so the even wider context for me is this has been maybe a recent 10 years or so, is trying to build rigorously conformal field theories or give some definitions of conformal field theories probabilistically. The prime example is, of course, that Colin has helped to make lots of progress on is the Liouville CFT. But there are also already maybe a bit before, there were very interesting approaches for finding also shadows of CFT already on the lattice level, finding representations of Virasoro algebra already on the lattice statistical physics models. Of course, there are some easy objects, the one that every physicist eats for breakfast, and Evelina has been talking about probably some things related to SLEs. And what are the type of results which we get? So I like this, that we are looking for kind of, basically, it's, you try to build this, to find this algebraic structure using probability to define it, etc. But actually, it has been also useful from a purely egoistic or probabilistic point of view. It has actually helped prove results in purely probability. So there are some integrability results, some explicit formulas that we before didn't know how to do. So there is something called the Gaussian multiplicative chaos. You will probably hear about when Remy gives his course. So this was conjectured via very, very different means with no mention of CFT, but was proved using CFT by Guillaume Remy. There's the famous proof of the TOCC formula for the 3-point correlations on the sphere. There are calculations of scaling limits of partition functions, boundary connection probabilities using methods inspired by CFT. As I mentioned, the 3-point correlation function. There's the shape of the CLE loop, which we only got grasps on once we realized the connection to Liouville CFT, etc. So this is one type of results which we are now able to do using this, trying to at the same time build up CFTs and using the structure from there. And the other type is more structural results, which I think have started to come later, but I am a big fan of. So this is, for example, really taking probability measures and building this algebraic structure of the CFT behind it. And so maybe the first example here was this, again, Liouville CFT, where they managed to construct representations of the Virasoro algebra and very natural, had very natural probabilistic interpretations of the generators of the spectrum, etc. And there has been one on the lattice, which was maybe surprising that you can do it already on the purely explicit on the lattice level. And finally, this structure on the CLE loop that Antoine talked about, which first of all, it's just beautiful to see that on this L2 space of the measure, you can find this natural structure, but it also helped them prove an important conjecture in the literature. Okay, and then the other maybe structural results are the conformal bootstrap results, which you can look from very probabilistic point of view as seeing as being able to now talk about some Markov type of processes also that are parameterized by surfaces. Okay, but this is all serious things, and as I said, I am not a very serious person, so I may be motivated, inspired by this a little bit. I've been trying to see for something simple. When you want to showcase simply that, okay, if you take these ideas, you can prove new things. It's actually useful, and this is the small story I would like to explain here. The story is around kappa equals to 4, and first I'd like to say why this is a very special value. Okay, first it's self-dual. You saw already easing was related to two different CLE, CLE3 and 16/3, and the kappa, there is this duality translation which swaps kappa and 16/kappa, and 4 is the only fixed point there. Okay, and actually another thing which it is, I have you've seen, and I've mentioned the Gaussian free field, and there's the Brownian loop soup. And the nice thing is that this CLE4 has a simultaneous relation to both. Okay, so all CLEs have some relation to the Gaussian free field and some relation to the Brownian loop soups, but they don't live all three naturally in some context. And these are objects with which we can calculate. Okay, GFF and Brownian loop soups are things with which we can calculate. So first, let me explain a bit more precisely this connection between CLE4 and the Gaussian free field. So Gaussian free field is this height function, and basically the only things you need to know about it are this way of constructing it, and then the fact that it's really Gaussian, and Gaussian variables we can calculate. Okay, there is explicit formulas for whichever points you want. And here this says how we can construct the Gaussian free field from nested CLE4. We start with the nested CLE4. For each loop, we toss a coin, plus or minus, and this means whether we go one step up or down. Okay, this one step has a specific height, which by convention is usually called 2 lambda. Lambda is a numerical value, pi over 2, so would have just, but because some people use different normalizations, one usually gives it as a parameter. So you do these tosses, and then you take another independent loop family inside. You do new tosses, and then you add them up. Okay, everything that goes up or down one step, you add them up, and then you continue doing this. And you can see that you could expect that there will be some picture that fixes or emerges. Because the loops, at least on the picture, they get smaller and smaller, and so the extra randomness you add is kind of more and more averaged out. And indeed, if you look at in some space of generalized functions, this sequence will converge. Okay, so this is the connection of GFF and SLE, and this is, in some sense, you can think see now where the idea of level lines come from, because here, I think I am describing some high level lines of constant height, and I'm describing the surface going from up to down and seeing whether I have to go at each step up or down. Okay. And as I said, there is another link which holds simultaneously, and which is linked to the critical Brownian loop subclusters. And this is a nice picture by Avelio Sepulveda. This says that actually you can really, although this Gaussian free field is not the pointwise defined object, it doesn't have a geometry, you can really actually talk about its decomposition into sign excursions in the following sense. Yeah.
What was the lambda with respect to the GFF?
So this is just a numerical value that depends on your normalization. If your normalization is, for example, that the covariance blows up like log, it will be pi over 2. But often people use 1 over 2 pi log, and it will be. So that's why it's used lambda, because there are two different normalizations, and then it's easier to. So there is only one value that makes it work, and this lambda is called the height gap. Because on a continuous surface, you would go up in the height continuously. Here, you really make these jumps in height. Any other questions? Okay, and so this is a picture by Avelio Sepulveda that shows different sign excursions of the free field now in different colors. And when we do this writing, what do I mean here? Well, you can write the GFF as really a geometric sum. we take some random fractals which have Hausdorff dimension 2, but have kind of this. If you look what is the right gauge function, it will be something like square root of log, and then you take this. You take these fractal sets. You take the natural fractal measures on them. This will give you some positive and negative measures on the domain. And then you just, when you flip independent signs to make them signed, and you add them up. Okay, and the outer boundaries of these will be CLE4 of these clusters, and these clusters themselves will have the law of critical Brownian loop subclusters. Okay, so they all live in the same thing, and this is actually, as Raul is here, the funny thing is. So this is something we had proved, and then we found your paper in the PRL with someone which found this, log fractal. And these are it's these sign clusters that are really this log fractal.
I don't understand the EI or random Minkowski measure. Or?
Yes. So they are. So I take this. You can think of it like this. So I have this. I have this loop soup clusters. Okay, so these are some fractal sets. You can actually find out that they do possess a Minkowski measure on them, and then which is supported on the set and deterministic with respect to it. And then you just flip plus minus signs, and then you add them up. Of course, you have to think how you add them up, because Gaussian free field is not a measure, so it cannot be written as a sum of finite sum of signed measures. But if you do it well, for example, in using the diameter of them, ordering them by diameter, this sum will converge and have the law of the shear. And we also show that there is actually a nice way to characterize it. There is really this kind of unique way using natural conditions to write this. Okay. And we will actually have to use it to do our calculations. Okay. And the other thing is that there are many discrete models that make the CLE4 appear critical 4 pods, Lupu 2.
We have another question.
Yes.
Kappa equal 4 is which central charge?
C equals to 1. Yeah. So this is this. But there is other reasons why this could be simplicitous. There's a plenitude of models that give it, but also the conformal field theory behind it is algebraically pretty well understood and actually very simple in the sense that you can really determine the structural constants, at least for 4-point functions, etc. Okay, so it should correspond to which is there is the point here to some compactified orbifold GFF, which still is much simpler than anything else we can think of.
What do you mean by especially? I mean, is it CLE4 or is it not CLE4?
What do you mean?
CLE4 only at one point?
Yes. At one point you see it in every way. So in the Ashkin-Teller, so if you think that this corresponds to Ashkin-Teller, then at this point the product spin has the same law of the single spin, and they all are represented by CLE4. Whereas for the other points, it's only the single spin that is somehow you can relate to CLE4. For example, if you take the easing point, and that is a little bit surprising because you would guess that it's CLE3 and 16 over 3, but you can also represent it. But the 4 pods is the simplest because of, from Ashkin-Teller point of view, because of this symmetry of product spin being the same as one spin being the same as the other spin. Yeah.
What do this tetrahedron and cube means?
What? Sorry.
What do this tetrahedron and cube meaning? What's the meaning?
These are in the category of more complicated objects for me. So there's this paper by Ginsberg where he tries to classify all C equals 1 CFTs, which I don't think he gives a complete classification. For example, there wouldn't be a Liouville type of field there. but he finds them as certain quotients. And then there is a continuous family of these quotients, which are these axes. And then there are three more complicated creatures. This is studying the algebraic structure of, so there is this current field that has more symmetries. And then when you mod it out, you will find different.
I have a question.
Yeah.
So on that line, so it's a Heisenberg, SL2, F5 VOA. I just try to understand. You said all these are related to C=1 conformal theories.
Yeah, so these all come from just the compactified free field. And this is what physicists call the compactified orbifold free field. And then there are some points which have extra symmetry. So there is also this, there is not only the Virasoro symmetry, but there is also like a current symmetry on some of these points. And these have some special symmetries. And here they put some special names. So this corresponds to the Kosterlitz-Touris transition in the XY model. So these are just like kind of special points that are known to be integrable, or but there is a whole one parameter family. And 4 pots is one of the special points. Okay. Okay, so you could hope for something simple, and let me try to convince you that there actually is something simple. There is something simple you can calculate based on a few observations. Okay, so the starting point maybe is these links, etc. But let's to really state it and prove it. Let's take a step back. We gave some fancy characterizations of these random sets, like with using some stationary independent properties. These were abstract characterizations that are very natural. But if you just want to understand the law of a random set, so it suffices to just take some points and calculate the joint probabilities that, you know, a number of points will be in my set. This is like, you see, if you want to tell what your set is, I basically have to just tell you all the points that are in the set. So probabilistically, when I want to understand a random object, I will just need to give you this. Okay, so you could, a naive person, you could ask, can we calculate such things that, you know, I take n points and they are all on, say, one CLE cascade? Okay, yes, you can do it, but the answer will be always 0, because actually these cascades, they have 0 Lebesgue measure, they're very, very thin. So, but there is a meaningful question behind this naive way of just looking at as a random set, which is, let's just renormalize and look at the renormalized probabilities. So this really would correspond to, at least heuristically, to continuum limits of such quantities that on the lattice level precisely encode the spin structure. And this has been done also for some cases like CLE 16/3 by Kami and co. Okay, so now I can state the main results. So we can show that these renormalized probabilities exist, and some tests can be calculated too. Okay, so for example, we can calculate the probability that you take the CLE4 in the unit disk, and the probability that 2 points are on the outermost casket of CLE4. So some remarks. Probably the existence of limits can be shown for all CLE kappa. So for SLE, this is something that was done a long time ago. But the calculation is really specific to kappa equals 4, and then probably is related to this simple CFT structure. I mentioned already that for nested, if one calculates it for nested CLE, this corresponds really to this spin correlation functions. And in the kappa equals to 4 case, the spin model would be the 4 pots. So we think we are also able to calculate the 4-point function on the sphere and you know, confirm your nice guesses on what the exact formula is to show them rigorously. But at the moment, it seems that there is still some work that needs to be done, unfortunately. But it's interesting work, so I think I will maybe comment on it. Okay, is the result somehow clear? So we have a specific formula that we fix 2 points in the unit disk. We ask that the CLE, outermost CLE4 cascade comes epsilon close to both, and we calculate this renormalized probability. Okay.
So
Yeah.
Can I say that this is a probability that these endpoints are in the same cluster?
Well, I mean, in this, so here it would be, I guess, usually nested CLE, so it wouldn't, on the sphere, we hope to also get that the 4 points are in the same casket, but you have to do a linear combination of things you can calculate. So this you will see in the proof that even for the disk, the first thing you get is that 2 points are on the same casket, and then you need another little trick to say that 2 points are on the outermost casket.
Mm-hmm.
So it's similar to for 4 points on the sphere, you would have the pairings, and you would need a linear combination. But we kind of see where it comes from. It just I can maybe comment on what's missing for the. Yeah.
You're not on your boundary condition. You're not on the terms. You're on the disk. It looks like me too.
Here we're on the disk, but we should be able also. I mean, there are some statements you can do in generality, in any generality that CLE4 is defined, and then there is the specific calculations which we can do at the moment in the disk, and we think we can do on the sphere for 4 points.
On which okay, so which boundary condition you have on the disk?
So this would be kind of wired boundary conditions. If you want the FK representation of 4 pots, it would be yes, wired. You would have a boundary cluster as well. So we are checking that 2 points are on the boundary cluster.
Yeah, because it's a 2-point function, but there's being with some boundary, you have some other information on the CFT level.
Yes,
I mean,
yes,
it's rich of information. This.
yes, yes. I will. Yeah, you will see that there is also this where you kind of take free and you ask. Then it's natural to ask. Then the 2 points will just tell you that you're on some casket. But probabilistically, maybe the more interesting one was exactly that you look at really this outermost CLE4 casket, and you're actually still able to calculate. So that was maybe a bit more surprising. Okay. Okay, so let's start with, and I just want to present you, you have, guys, you have your way of calculating things, and that'd be actually interesting to know how you would calculate this 2-point function in your language with fusing and using fusing. But let me show how we can. Okay, first, there is a simple calculation where you want to do just 1 point, for example, on the casket, because this is already an observation made by 10, 15 years ago by Schramm, Sheffield, and Wilson, is that you can construct this CLE continuously via some SLE exploration processes. And using this exploration process, you can define a martingale which has a natural stopping condition exactly when you close a loop around it. Okay. So using this, you can actually, and the time will be related to how close you get to the point. So using this, you can actually calculate exactly the probability that I get epsilon close to the CLE4, because you just look at the probabilities distribution of this exit time. Okay, so this, but it's very hard to see how you could do it for several points at the same time. If you ask, it could come close to many points. Okay, you could still define a process which you stop when it comes close to at least one of the points, but there is no natural way to do it for both. So where do we get the integrability? Okay, so the first thing.
Can you comment? maybe stupid question, but you write the conformal radius, so D minus CLE4 is the disk.
Yes, so if you start this, not necessarily this, but it will be, if I start the exploration, it will always be a simply connected domain here. So there is a
project.
Yes, I will never, I'm always exploring in a connected way, so there is always a well-defined conformal radius.
Because in the example you showed before, they were like set of loops.
Yes, yes. Here I start in the simply connected. So this also shows that if you would even for one point, if you go outside of simply connected, it.
Then I'm confused. This is SLE or CLE?
So this is SLE, but you construct CLE using it. So if you want, you know, to know the distance of this from CLE, you just need to go and construct a loop of CLE that surrounds it. Because there will always be a loop surrounds, and you just need to construct that. And this you can maybe imagine that you can construct by, in the SLE4 case, you will construct it using such a process that just does loops, but always remains continuous. And then there is a martingale that you observe from here, which is basically kind of the expected height or the height of the domain after part of the excursion.
This is specific to kappa equals 4?
No, so this is not specific to kappa equals to 4. There's the martingale is the easiest in the kappa equals to 4 case, but this works for any. They actually, this what they prove this for any kappa. So this still is something which works for all kappa. So this now is something that works for loop sup or loop sup intensities. I guess you take loop sup clusters and you ask whether there is a cluster that separates 2 points from each other. Okay, this comes back to a Brownian calculation as a Brownian loop sup calculations, and so sorry, this is just Lupu, and this is one of the basic things. So one observation that we made was that you can actually calculate this limit when epsilon goes to 0 precisely, and you obtain an explicit formula. Okay, and this would what this would correspond to is in the physics literature is a correlation of twist fields, but for a GFF with infinite compactification radius. Okay, so there's an explicit calculation for that. So this is what something the quantity which appears for 4 points in the sphere, for example, in this old papers, strings on orbifolds by Frieden, Schenker, Dixon. So this is one way to see these formulas appearing, and okay. But how do we get from there to CLE4? Well, there is one observation which I didn't tell you. I told you that it's important that the CLE4 is related both to GFF and Brownian loop sup. I gave you some way of connecting them, but actually I didn't explain you the key ingredient, which is how the critical Brownian loop sup itself is connected to CLE4. So in fact, you can construct the Brownian loop sup cluster by just iterating CLE4s. Okay, so I start from an outer boundary, which itself is CLE4, and then I start iterating. I have this labels plus minus 1, or plus minus maybe I put 2 lambda, then they go plus minus 4 lambda, etc. So for each point, I'm going to define some walk of labels. Okay, and I will just continue each of these walks until I get, so it starts actually, sorry, it starts from 2 lambda, then it goes to 0, 4 lambda, etc. And I continue all these walks until they get to 0. Okay, so there is a way of using this nested CLE4 to construct a Brownian loop sup cluster. And this in particular gives us a way to translate this information on on Brownian loop subclusters, separating points to actually points being on certain CLE4 cascades, where these cascades we choose depending on the labels. Okay, so this gives a first integrability result for CLE4. And in this case, it would be what? It would be exactly the same thing, that there are the 2 points are not separated by an excursion cluster. And the only way this is possible is that they are in the dual of an excursion cluster, which is that they are in a CLE4 cascade, but in a CLE4 cascade that has a specific height. Okay, so the heights will be, they will go from 0, 2 lambda, 4 lambda, maybe 2 lambda, etc. They will form a random walk, and we only look at cascades where this value would be 0. So this is some random collection of cascades in the whole nested CLE4. Okay, so this would be the first formula that we have, but it's certainly not the one we want to have, right? Because you would want to have the probability that they are either on every cascade, or every odd cascade, or every even cascade, or that they are on the outermost cascade. Here we have just some random iterations. But even in this formula, there is something interesting. There is already some nice elliptic integrals that appear. So it's not an entirely trivial formula. Maybe I'll try to say where these integrals come from. They come from conformal maps that you all like. Okay, so we cannot calculate with Brownian. I said we can calculate with Brownian loop sub. Well, we cannot calculate really in the disk. We have to go to somewhere nice where we can calculate, which would be, for example, annulus, because then the Brownian motion there really orthogonalizes. There are 2 independent directions. But how do you go from this disk with 2 branch points to an annulus? So this is a nice exercise in conformal maps. There is one observation you make quite quickly, which is that if you look at an annulus, then you get the double cover of with branch points of an ellipse. Okay, so this is a very classical, this you can figure out. And then you get a bit more curious when you see this formula for going from the disk to an ellipse. Okay, so this, for complex analysts, they learn it in kindergarten, but if you're a probabilist, you will have to think about it a little bit, where and how to come up with it. Okay, and actually there is a nice way. The elliptic integrals come from the Schwarz-Christoffel mapping, where you take the half disk with the 4 marked points and you go to a rectangle. Okay, and this is kind of what is sufficient, because then going from rectangle to half an ellipse is already simple, and then from the full disk to there you just do a reflection. Okay, so this is the origin of the elliptic integrals. But maybe the more interesting point is how to go from these random iterations to now deterministic iterations. Okay, so as I said, to what we computed, we had this nested label CLE, and we looked where these labels hit 0. Okay, and we would want to transfer it to say all cascades, or at least all odd cascades, or only the first cascade. Okay, and so the probabilistic question is very simple. How do you go from the 0 set of the simple random walk to say all indexes, or all even or all odd indexes, or only the index 0? Okay, and this comes out that there are 2 little lemmas, which maybe you don't even call lemmas, that 2 little observations you can make. One is that, okay, let me look at the simple random walks, and I consider the infinite measure by just adding up its starting point. Okay, and then you notice that now the probability that Sk is equal to 0 will be 1 for all points. Okay, so this is just a little observation to do. And on the other hand, then you think, okay, how do I get the first one? Well, for that, you consider a sign measure on simple random walks, and you use the fact that when you're outside of 0, even and odd indexes will actually cancel out. Okay, so if you I don't know if I put things correctly there, but maybe I should have started from 2 set and 2 set plus 1. But in basically, this is how you get only the first index. And this, I recall, is meaningful in our context, because how can I start change the starting point of my height? I will just add boundary conditions on my disk. Okay. And physically, it just corresponds to looking at actually the compactified field. And that is the nice thing in the disk, that I can introduce this compactification by just changing boundary conditions on the outer boundary. Okay, and then what you get is really when you take the nested CLE4 in the unit disk, you obtain such a formula. So this would be that the points are 2 points are on the same CLE4 casket, and it's also given by a very simple probabilistic correlation actually of the cosine and the sine of the free field. If you just take cosine, you actually just get odd caskets. If you just take sine, you get just the even caskets. If you add them up, you get both. So C3 should be in front of both of those. Okay, so this calculation, you know, what we did was a heavy way to calculate this thing, which is a straightforward calculation. But it's funky that it works. And when you want to get the one for the usual outermost CLE4 casket, you do a different summation and you end up with such a formula. We have checked whether the formulas are coherent. If you change the compactification radius, you should get correlation functions of easing. You do get them, so everything is. And I will end here. I think it's time to do that.
Are there questions?
So the input you mentioned on this Brownian loop with the 2-point function, was it computed using this like gauge Laplacian or something?
The equivalence between the kind of topological conditioning and the formula of exponential of the measure comes from this work of Titus, where he used his case-twisted Laplacian. But the actual calculation is really just a Brownian loop soup calculation, just a calculation with Brownian motion, basically.
Okay.
And it's just, you cannot do it in all cases, but this calculation you can do for 2 points on the disk, you can do it for the 4 points on the sphere. You can also find some maybe partition functions using that.
Have you checked that this 2-point function? So you can modify the compactification radius?
Yes. So
you are in this orbifold line?
Yes.
And this function has been computed in the CFT?
So I don't find so many things in the CFT that do calculations on like simply connected domains, but mathematicians have done it for the easing model, and for the easing it fits.
Yeah, for the easing square, yeah.
No, not easing square. You can, this gives a computation for a single easing, not for the easing square. So easing square would be a calculation using cosine, which is trivial. But single spin, if you don't use the doubling trick, you will have to find another way to calculate. And here this is done by resumming these things in a different way. And this you can check that you get exactly the same formula. But what I would be interested in is really like what is the physics way to get this formula. because here we have it's kind of this little trick. I don't know what this trick corresponds to. Like the first one, I can imagine better than the second one. I guess in both cases, it has to come to some, I don't know, funky disconformal blocks, and some coefficients are just signed in one of the cases. But it would be actually nice to see it also from this physics perspective. At the moment, it's just like a probabilistic trick to find the right resummations.
There are more questions? Okay, so thank you, Anna, again.